There's a planet in our solar system where temperatures plunge to minus 224 degrees Celsius. That's colder than liquid nitrogen, colder than anything humans have ever experienced, colder in fact than any other planet orbiting our sun, including the one that's even farther away. And that's the part that doesn't make sense. We all learned the same simple rule in school. The farther from the sun, the colder it gets. Mercury is scorching, Venus is an oven, Earth is comfortable, Mars is chilly, and then you keep going outward. Jupiter, Saturn, Uranus, Neptune, and each one should be colder than the last. Simple, logical, wrong. The coldest planet in our solar system is not the most distant one. It's the second most distant, and the reason it holds that record has nothing to do with how far it sits from the sun. It has to do with something that happened billions of years ago, a catastrophic event that stripped this giant of its internal fire and left it slowly freezing in the dark ever since. This is the story of Uranus, and it's far stranger than a temperature record. If you could somehow stand on the cloud tops of this world, which you can't, because there's no solid surface, the sun would look like a bright star. Not a disk, not a glowing sphere filling part of the sky, just a point of light, roughly 400 times dimmer than what we see from Earth. It wouldn't warm your face. It wouldn't cast a sharp shadow. It would simply remind you that a star exists somewhere in the distance. The numbers make this brutally clear. Earth orbits the sun at about 150 million kilometers. Uranus orbits at 2.9 billion kilometers, nearly 20 times farther out. And because the intensity of sunlight drops with the square of the distance, Uranus receives roughly 1/400th the solar energy that Earth does. Double the distance and you get a quarter of the light. Go 20 times farther and you get almost nothing. But distance alone doesn't explain why Uranus is colder than Neptune. Neptune orbits even farther out, about 4.5 billion kilometers from the sun. It receives even less sunlight, and yet Neptune's atmosphere is measurably warmer than Uranus's upper clouds. This is where the story stops being about geography and starts being about the internal life of a planet. Every giant planet in our solar system was born hot. When a planet forms from a collapsing cloud of gas and dust, gravitational compression releases enormous amounts of energy. The young planet glows with internal heat, and in most cases, that heat persists for billions of years. The planet slowly radiates it away, but the process is gradual, so gradual that even after 4.5 billion years, most giant planets still shine with residual warmth. Jupiter radiates nearly twice as much energy as it receives from the sun. Saturn radiates about 1.8 times more. Neptune, the most distant giant, puts out 2.6 times more energy than it absorbs from sunlight. These planets are still cooling from their formation. Their interiors are active. Heat rises through convection, warming the atmosphere from below, driving storms, generating wind. Uranus does almost none of this. Its internal heat output is barely distinguishable from zero. It radiates essentially the same amount of energy it receives from the sun, no significant excess. It's as if the planet's internal furnace shut down, as if something happened long ago that robbed it of the thermal energy every other giant still possesses. And this is what makes Uranus the coldest planet. It's not just far from the sun, it's also cold from the inside. It gets minimal energy from the outside and generates almost nothing from within. The upper atmosphere loses heat faster than it can be replaced from any source. The result: cloud top temperatures of minus 224 degrees Celsius, the lowest of any planet in the solar system. So what happened? Why is Uranus thermally dead while its near-twin Neptune remains active? To answer that, you need to look at the single most obvious oddity about Uranus, its axial tilt. Every planet in the solar system rotates on an axis that's roughly perpendicular to its orbital plane. Earth is tilted at 23.5 degrees, which gives us our seasons. Mars is similar. Jupiter is nearly upright at just 3 degrees, but Uranus is tilted at 98 degrees. It's essentially lying on its side. It rolls around its orbit like a ball, with its poles alternately pointing directly at the sun. Nothing in normal planetary formation produces a tilt like that. Planets form from spinning disks of material, and the angular momentum of that formation process keeps them rotating more or less upright. Something knocked Uranus over. The leading hypothesis is a giant impact early in the solar system's history, during the chaotic period when protoplanets were still smashing into each other. A body roughly the size of Earth slammed into Uranus. The collision was powerful enough to tip the entire planet onto its side. But it may have done something even more consequential than changing the tilt. It may have disrupted Uranus's internal structure in a way that shut down its heat transport system. Here's how that works. In a normal gas giant, the interior is hot and the exterior is cold. This temperature difference drives convection. Hot material rises, cool material sinks, energy moves outward. It's the same process that drives weather on Earth, currents in the ocean, and circulation in a pot of boiling water. But if a massive impact scrambled the internal layers of Uranus, mixing the hot core with cooler outer material, creating stable stratified layers where dense cold material sits below lighter, warmer material, then convection stops. The interior becomes thermally stratified. Heat gets trapped deep inside, unable to rise. The upper atmosphere is cut off from the internal energy supply and begins to cool. Over billions of years, this cooling has made Uranus the frigid world we see today. The energy may still be locked deep inside. The core could be genuinely hot, but it can't reach the surface. The planet is wearing an insulating blanket of its own disrupted interior, and its atmosphere is paying the price. This is why Uranus is colder than Neptune despite being closer to the Sun. Neptune retained its normal internal structure. Heat rises, atmosphere stays warm. Uranus lost its convective engine. Heat stays locked below. Atmosphere freezes. One ancient collision, and the entire thermal history of the planet changed forever. Now let's talk about what that cold atmosphere actually looks like. Because Uranus is deceptively boring at first glance, and spectacularly weird once you look closer. When Voyager 2 flew past Uranus in 1986, the only spacecraft to ever visit, it sent back images of a pale blue-green sphere that looked almost featureless. No bands, no storms, no dramatic cloud formations, just a smooth, uniform ball of gas. Compared to Jupiter's raging storms and Saturn's elegant bands, Uranus looked like the most boring planet in the solar system. But that turned out to be a matter of timing. Voyager 2 arrived during a period when one of Uranus's poles was pointed almost directly at the Sun. The illumination was relatively even across the visible hemisphere. There wasn't much contrast to see. The atmosphere appeared calm. Years later, as Uranus moved through its orbit and the geometry changed, ground-based telescopes and the Hubble Space Telescope began detecting cloud features, bright spots, dark bands, evidence of storms forming and dissipating over months and years. The atmosphere wasn't dead, it had just been sleeping during Voyager's visit. And the winds. Despite having almost no energy input, Uranus generates winds up to 900 kilometers per hour. That's close to the speed of sound in Earth's atmosphere. These winds blow primarily along lines of latitude, creating east-west jet streams similar to those on Jupiter and Saturn, but much harder to see because the cloud features are so faint. How does a planet with almost no energy drive winds that fast? The answer lies in the extreme seasons. Because Uranus is tilted on its side, its seasons are unlike anything else in the solar system. During 1/4 of its 84-year orbit, the North Pole points toward the Sun and receives continuous illumination for about 21 years straight. Meanwhile, the South Pole sits in total darkness. Then the situation gradually reverses. This creates enormous temperature differences between hemispheres, differences that build slowly over decades. And those temperature gradients drive atmospheric circulation, even though the total energy involved is small. The winds on Uranus aren't powered by intense heat. They're powered by patience, by decades of slow asymmetric warming that eventually sets vast masses of frigid gas into motion. Everything about Uranus happens slowly. Seasons last longer than most human lifetimes. Weather patterns evolve over years. If you were born at the start of spring on Uranus, you might not live to see summer. Now let's go deeper. Beneath the visible clouds, beneath the frigid upper atmosphere, where temperatures hit that record -224 degrees, Uranus becomes truly alien. There's no surface, no ground, no boundary between sky and planet. As you descend, the atmosphere simply gets denser. Gas becomes thicker, heavier. Pressure climbs, and the composition starts to change. The upper atmosphere is mostly hydrogen and helium, with about 2% methane. It's the methane that gives Uranus its distinctive blue-green color. Methane absorbs red wavelengths of light and reflects blue, painting the planet in that pale aquamarine tone. But below the hydrogen-helium layer lies what scientists call the ice mantle. And this is where things get genuinely strange. The term ice is misleading. This isn't frozen water in any form you'd recognize. It's a super hot, super dense mixture of water, ammonia and methane compressed under millions of atmospheres of pressure. The temperature in this region can exceed 1,000 degrees Celsius, and yet the material behaves like nothing on Earth. Under these extreme conditions, water enters what's known as a Superionic phase. The oxygen atoms lock into a rigid crystal lattice, like a solid, while the hydrogen atoms break free and flow through the lattice like a liquid. It's simultaneously solid and liquid, a crystal that conducts electricity, a form of matter that exists nowhere on Earth's surface and can only be briefly recreated in laboratories using diamond anvils and high-powered lasers. These Superionic ice layers are almost certainly responsible for one of Uranus's most baffling features, its magnetic field. Earth's magnetic field is generated by convection currents in a liquid iron core. The field is roughly aligned with the planet's rotational axis and emerges from near the geographic poles. It's relatively symmetric and stable. Uranus's magnetic field is none of these things. It's tilted 59 degrees from the rotational axis. It's offset from the planet's center by about a third of Uranus's radius. And it's wildly asymmetric. The field strength varies dramatically depending on where you measure it. As the planet rotates, the magnetic field wobbles and tumbles through space, creating a magnetosphere that looks like it was designed by someone having a bad day. This bizarre geometry makes sense if the field is being generated not in a central metallic core, but in the Superionic ice mantle, a shell of electrically conducting material that doesn't sit at the center of the planet. The currents flowing through this off-center, irregularly shaped region produce a magnetic field that's inherently lopsided and tilted. So deep inside the coldest planet in the solar system, there's a layer of electrically conducting hot ice generating a crooked magnetic field. The contrast is almost absurd, -224 degrees at the cloud tops, over 1,000 degrees in the ice mantle. Two completely different worlds separated by a few thousand kilometers of increasingly compressed gas. And there's one more exotic possibility hiding down there. At the very deepest levels of the ice mantle, where pressure reaches millions of atmospheres, methane molecules can be torn apart. The carbon atoms, freed from their hydrogen bonds, are squeezed together under unimaginable force. And under those conditions, carbon does what carbon does at extreme pressure. It forms diamonds. There may be a steady rain of diamonds falling through the deep interior of Uranus, crystallizing out of the atmosphere at extreme depth, sinking slowly through the dense surrounding material toward the core. Not tiny crystals, potentially chunks large enough to qualify as gemstones by any earthly standard, falling like hailstones through a sea of hot, electrically conducting ice. We can't directly observe this. It's happening thousands of kilometers below the visible surface, buried under crushing pressure. But laboratory experiments using lasers to compress methane at Uranus-like conditions have confirmed that diamond formation is not only possible, it's expected. So can anything live here? In a world where the surface temperature would freeze any known organism solid and the deep interior would crush and cook it simultaneously? Almost certainly not. Not by any biology we understand. The upper atmosphere is far too cold for the complex chemistry that life requires. The deep interior is far too hot and pressurized, and there's essentially no liquid water in any accessible form. But Uranus matters for the question of life in a broader sense. When we look at exoplanets, orbiting other stars. A huge number of them appear to be ice giants similar in size and composition to Uranus and Neptune. They may be the most common type of large planet in the galaxy. Understanding what Uranus is like, its temperature structure, its atmospheric chemistry, its energy balance, helps us evaluate whether similar worlds elsewhere might be more or less hospitable. And here's the deeper significance of the coldest planet. Uranus isn't just a curiosity, it's a preview. Our sun is middle-aged. It has about 5 billion years of hydrogen fuel left. After that, it will expand into a red giant, swallowing Mercury, Venus, and possibly Earth. Then it will shed its outer layers and collapse into a white dwarf, a dim, slowly cooling ember. When that happens, the entire solar system will get dramatically colder. The outer planets will receive almost no energy from the fading sun, and whatever internal heat they still possess will eventually radiate away. In the very distant future, every planet in our system will resemble Uranus. Cold, dark, thermally exhausted, still orbiting, still rotating, still carrying moons and magnetic fields and atmospheres, but drained of the energy that once made them dynamic. Uranus is already there. It arrived at this state billions of years ahead of schedule, thanks to whatever ancient catastrophe disrupted its interior. It's a planet that has already experienced the thermal death that awaits the rest of the system. When we look at Uranus through a telescope, we see a pale blue dot. Quiet, unremarkable, easy to overlook. But behind that calm exterior is a world of extremes. Winds howling at 900 kilometers per hour through an atmosphere that barely has enough energy to stir. Exotic ice conducting electricity thousands of kilometers below the surface. A magnetic field tilted and offset like nothing else in the solar system. Diamond rain falling through superheated slush in the deep interior. And a temperature record that defies the simple logic of distance from the sun. Uranus is not the most dramatic planet. It's not the biggest, the brightest, or the most photogenic, but it might be the most important for understanding what happens when a planet loses its fire. When the internal engine shuts down, when the heat runs out and all that's left is a slow, cold orbit through weakening starlight. Every giant starts hot. Every giant eventually cools. Uranus just got there first, and in the silence of that cooling, in the icy winds and the diamond rain and the sideways spin of a world that was knocked over before life on Earth even existed, there's a lesson about the universe itself. Heat is temporary. Cold is the destination.